Although trigonometry can reportedly be traced back to ancient Egypt, Mesopotamia, and the Indus Valley of ancient India, more than 4,000 years ago, the first recorded use was by the Greek mathematician Hipparchus around 2,000 years ago, and it was developed further by the Egyptian mathematician Ptolemy around 250 years later. Although initially used for navigation and to study astronomy, the ancient Sinhalese in Sri Lanka also used it when constructing water reservoirs to calculate the gradient of the water flow. Today, applications of trigonometry extend into many fields, including music theory, acoustics, satellite navigation, sound and light waveforms, engineering, seismology, and many, many more. The term trigonometry, although probably not used until 1595, comes from the Greek terms tri, meaning three, gon, meaning angle, and metri, meaning to measure. In this series, we will be dealing with the trigonometry involving right-angled triangles only. So what is the main idea behind trigonometry? To understand why it works, you need to at least understand the basics of mathematical similarity, which is the study of shapes that are enlargements or reductions of each other. All you really need to appreciate is that when a shape is enlarged or reduced, it doesn't change shape, just size. The angles between the sides don't change, just the lengths of the sides change, by the same scale factor in all directions. If one side is doubled, then they're all doubled. Think about enlarging a photograph. If we double the width, we also double the length. It wouldn't look right if we only doubled the length. Looking at our triangles, since all sides have been multiplied by the same factor, then the ratio between any pair of sides in the original triangle will remain the same in the enlarged or reduced triangle. This pair will always equal 3/5, no matter how big or small the triangle is, but only while these angles don't change. Now this angle is about 36.87 degrees, which means this one is about 53.13 degrees, since the angles in a triangle always add up to 180 degrees. Obviously, this means that once you know one of them in a right triangle, then you really know the other one as well. And here we have the simple secret behind trigonometry in right-angled triangles. Whenever we see this angle, 36.87 degrees, although that's not its exact value, then we know that the ratio of these two sides in that triangle will equal 3/5. But why is this important? Well, if we know any two of these three values in the right triangle, then we will be able to work out the third value. I show you how this is done in other videos in this series. Do you think you can work out the height of this tree? Before we can learn to do this using any side and any angle in any right-angled triangle, we need to understand the ratios between the sides and their connection to the known angle. Let's investigate by looking at a special case where we know the exact angle size. In this example, drawn to scale, I have marked one angle and two of the side lengths with their exact values. This time, the ratio of the two sides is exactly 1/2. This will be true in any right-angled triangle with a 30-degree angle. No matter how big or small the triangle gets, if it has a 30-degree angle here, then the ratio of those two sides will always be 1/2. Can you guess the missing side length in this enlargement of the same triangle? Of course it has to be 10, because 10 over 20 equals 1/2. And it remains true for any right-angled triangle with the 30-degree angle in it. This is what trigonometry is really all about. But once we change the angle, even just a little bit, the ratio no longer equals exactly 1/2. At 31 degrees, it's now about 0.515. And for 30.1 degrees, it's about 0.5015, very close to 1/2. Fortunately, all the correct values for any angle have been worked out, and they are stored in your calculator. We will see where later. To help us use these special relationships in right-angled triangles, it is useful to name and label all the sides and angles instead of simply saying this side and so on. We will also give special names to the ratios that we make. Hopefully, you've already learnt about Pythagoras' theorem, and you know that the longest side in a right-angled triangle is known as the hypotenuse. It is always opposite to the right angle, because the right angle is the largest angle possible in a right-angled triangle. A side note, the smallest side will also be opposite the smallest angle. These facts are true in any triangle, not just right-angled triangles. In our example, the smallest side was opposite to the 30-degree angle, but we don't really care that it's the smallest, only that its position is opposite to the 30-degree angle. If the angle was, say, 50 degrees, it wouldn't be the smallest angle anymore, but it would still be the opposite side. We already know the hypotenuse is opposite to the right angle, so there is only one remaining side to label. It is sitting right next to the reference angle, so we refer to it as the side adjacent to the angle. Here we have step 1 in using right-angled trigonometry. We must label the sides according to their position in reference to the angle we wish to use. Now we can refer to the sides used in our ratio more conveniently. The ratio in our example came from the side opposite to the 30 degrees over the hypotenuse. The adjacent side was not given to us, so it could not be used in this example. We have discovered that no matter how big or small the right triangle is, for a 30-degree angle, the opposite side divided by the hypotenuse will always be exactly 1/2. Now that we can easily refer to the sides used in the ratio, we can go one better. For convenience, we can give the ratio its own name. This ratio is known as the sine ratio. Since the opposite side is determined by which angle we are referring to, then it makes sense that we should include the angle when writing down the ratio. So we write it like this. More simply, sine A equals opposite over hypotenuse. Notice that sine has been abbreviated to SIN, but it is still pronounced sine. Since there are 3 sides in a triangle, there must be more than one way to get a ratio of 2 sides. We could have used the adjacent side instead of the opposite side. We can now compare the adjacent side over the hypotenuse, and we give it its own name. It's known as the cosine ratio, or cos for short. It's called cosine because it is connected to sine. Can you see why? If we swap to the other acute angle, then the names of the opposite and adjacent will also swap. In our example for 30 degrees, if we swap to the other acute angle, which is 60 degrees, its adjacent side is the same as the side opposite to the 30-degree angle. So we get a ratio of 1/2 again. The cosine ratio of 60 degrees is really the same as the sine ratio for 30 degrees. It will always be true. The sine ratio for one angle in the triangle will always be the same as the cosine ratio for the other acute angle, and vice versa. The two angles will always be complementary, meaning their sum is 90 degrees. So cosine really stands for complementary sine. You don't need to worry about this if it's not clear, but at least you know the co in cosine stands for complementary. Now, can we find another possible pair of sides to compare? We could turn the ones we already have upside down, but that is really the same ratio in the reverse order. And you don't need to do that unless you do higher powered mathematics in senior school. However, there is one more pair of sides we could use. If we ignore the hypotenuse this time, we have a ratio comparing the opposite side to the adjacent side. We call this ratio the tangent ratio, or tan for short. Again, the reciprocal or upside down version is not needed, so there are no more possible pairs. And now we have our three trigonometric ratios or trig ratios that you will need to know. Sometimes we might use a variable to label the angle inside the triangle rather than referring to it by its vertex. In mathematics, we often use Greek letters. This Greek letter is known as theta. We can also abbreviate our side names to hyp, op, and adj. Now we can summarize what we have learnt. You might even go as far as simply using h, o, and a. The sine ratio is the opposite side over the hypotenuse. The cosine ratio is the adjacent side over the hypotenuse. And the tangent ratio is the opposite side over the adjacent side. Be aware that it is also common to write the angles in parentheses, like this. Most calculators will do it this way. You need to know these ratios well before you can use them for solving trigonometric problems. So let's look at some memory aids to help you. Firstly, the acronym SOHCAHTOA shows the first letter of the ratio name and the correct order of the sides for each ratio, especially if you write it like this. And here is a simple mnemonic to help remember the acronym. Some old horses can always hide their old age. There are many other versions, so pick one that suits you, or you could even make up your own. Depending on the information provided, there are different ways you might be asked to write the value of each ratio. Let's do some examples. Following the recommended procedure, first we label the hypotenuse, then the side opposite to the angle we are using, which is alpha in this case, and finally we are left with the adjacent side. Now we can read the values of the three ratios. Sine alpha is equal to 20 over 52, which simplifies to 5 over 13. Cos alpha is the adjacent over the hypotenuse, so it's 48 over 52, and this simplifies to 12 over 13. Finally, tan alpha is the opposite side over the adjacent, giving us 20 over 48, which simplifies to 5 over 12. We could also give decimal equivalents, but keep in mind that if we round the values at all, they are no longer the exact ratio values. In example 2, we are given variables as the side lengths. We label the sides as before, hypotenuse, opposite, adjacent, and now again we can easily read the values. The angle this time is the Greek letter beta, and we have sine beta is equal to b over c. Cos is a over c, and lastly tan beta is b over a. In our last example, we have both angles alpha and beta labelled, so we will need to do the ratios for both angles. Let's do alpha first, labelling the sides as before. This time we only have the vertices labelled, so we will simply refer to them to identify each side. We end up with sine alpha equal to tx over xq. Technically, interval lengths should be represented with a line interval above them, like this, but it's quite common not to do so, so we will leave them off as well. Cos alpha will be qt over xq, and tan alpha is tx over qt. Now we move to angle beta. The hypotenuse won't change, but the opposite and adjacent sides will swap positions. To avoid confusion, you might elect to redraw and relabel the triangle like this. Sine beta becomes qt over xq, cos becomes tx on xq, and tan beta is qt on tx. Did you notice that the sine and cosine merely swapped from the answers we got for alpha? And tan for beta is the reciprocal of the tan for alpha. It's flipped upside down. If you know these tricks, it will save you time in redrawing and relabeling the triangle. To end our video, have a look at our 3 abbreviated ratio names. Have you seen them anywhere else before? They're written on buttons on your calculator. As a brief introduction, these buttons store the ratio values for every possible angle. But be warned, your calculator must be set to degrees to get the correct values. Remember that we found the sine ratio for 30 degrees to be exactly 1/2? Pressing the sine button, typing 30, then pressing equals gives us 0.5, which is of course 1/2. To learn more about using these buttons, be sure to check out the second video in this series.